Hello, my name is John Shramsky. Today we're going to talk about energy, design theory, and what this means for the future of energy and materials modeling. Thank you for attending. If you have interest in the materials that I present today, I encourage you to look for this first paper that was published last year, and we'll cover some of the topics that I'll introduce to you today. And then, of course, the rest of the materials that I'm talking through today are the subject of a manuscript that's in advanced prep at this time and will be coming out shortly. So I encourage you to also look forward to that. This is an energy-based presentation and an energy-based theory. This is in contrast to the more typical sustainability science-oriented approach, which is a materials-based approach. If you would like an idea of a materials model to consider as in contrast to an energy model, then one good paper, and there's many good papers out there, but one good paper, of course, is The Planetary Boundaries, put forth by Rockstrom, Stefan, and others. Limits to Growth would be another good example. So I'll talk about the difference between an energy approach and a materials approach in this presentation, and I'll talk about it mainly conceptually, simply because there is not enough time to get into the numbers and the case studies. Those will, of course, be available in the paper. So I encourage you again to consider looking for that. Okay, so quickly, this is the third. You can keep an eye on the number of slides that I have as I work through my presentation down here in the lower right-hand corner. This happens to be my last slide, 12 of 12, but I'm going to show it to you on the front end here so you have an idea of where we're going. If you consider the energetics of our current acceleration, then what we're going to put forth logically is that modern design theory as we know it, which is to improve efficiencies of operation, is no longer applicable and no longer workable. And the future of design theory will be to have to flatten this energy curve. So we will talk about the extent of this and what this means for Thomas Kuhn's incommensurability thesis, as he put forth in The Structure of Scientific Revolution. So the things that I'm going to talk through here for the next 10 minutes are going to lead up to this slide, and this slide will be more informed to have a discussion about these statements that I'm showing you here. All right, so with that in mind, let's talk about energy. Let's talk about design theory, and then what that means for some of our near-term considerations. First of all, when I use the word energy, it can mean many things to those in this audience watching this presentation, just because we all research many things with regard to energy. So in order for us to be speaking from the same context, let me take 3 minutes here and make sure that we're all speaking and thinking of energy in the same light, as we then use that to lay the foundation and talk about design theory and modeling theory. So the original energy gradients in the formation of the planet are shown here. Solar energy, the planet was just a moonscape, and we probably had some wind due to some primitive atmospheres that existed from time to time through the millennia, geothermal heat from the planet cooling, gravitational forces, some minor electrical gradients, and nuclear materials, but nobody around smart enough to harness those. As we come forward through 4.5 billion years of evolution, we added some additional organic energy gradients. First, we had single cell, simple life prokaryotes. After about 1.5 billion years, these evolved into multi-cell eukaryotes. And then ultimately we hit the Cambrian explosion and a couple other eras over the course of about 400 or 500 million years, primarily from the spread of photosynthesizers. And we acquired biomass. From biomass, of course, we get fossil fuels. We have animals in the animal kingdom. We have proven to be good at harnessing these animals for their energetic outputs, beasts of burden. We have the hydrosphere, which we're pretty good at harnessing, and we have all of the energy gradients associated with the oceans, with the currents, the tides, the waves. So all of these energy gradients exist because of evolution, plus our original energy gradients and our only true renewable energy, technically, solar energy. And this represents the energetics of the planet, all the energies that we're aware of that are capable of using in the near future are shown here. So now we're all on the same page. If I juxtaposition these over the top of the planet, we get a better idea of how all of these are not separate, but in fact, they all work together, as you see the planet in the background, to promote net primary production, which is the yearly pulse of new biomass that's produced through photosynthesis. This adds to the biomass. If we leave this unadulterated for 400 or 500 million years, we'll get fossil fuels, and the process will continue, storing this energy from solar energy. The problem with this is that this point here now is clearly exquisitely balanced. I could think of a better word, but more balanced in the broadest sense. Humans, on the other hand, if I go back to the original energy curve that I showed you at the beginning of the presentation, are consuming energy at an exponential rate. Right now, we're at 580 exajoules per year. All right. The main point here is that when you consider the balance and the growth of what's occurring over here, and you compare it to the numbers that humans are currently achieving, this is too big of a number, and we could spend considerable time talking about this, but just to give you some examples, put it in context, this number is actually 17% of net primary production. So we're not burning 17% of net primary production every year, but this number represents 17%. So we're already up burning numbers that are at a global scale. It's actually 3% of the estimated total chemical energy in the global biomass of the marine and terrestrial systems. Most of this is in forests. So this is too big of a number. Humans are burning too much energy. All right. The other point that I would like to make is that energy is ability to cause change. We know this. This is the definition of energy, right? So when you discharge energy, you cause change. And therefore, to make sure we're all thinking of this the same way, energy discharge, of course, is a forcing function. So there's a reason why when our energy discharge curve looks like this, near exponential, right? That our activities are also near exponential, because this is the discharge and we're causing change with this, with transportation, paper production, telecommunications, fertilizer consumption, etc. But this leads to the biophysical reactions on the planet, which are also exponential shaped. Energy discharge is a forcing function. As long as we're going to have an exponential energy discharge, whether this is renewable or non-renewable energy, it doesn't matter. So the energy transition only gets us so far, okay? But with an exponential energy discharge, we're going to have exponential effects in the environment. Until this exponential curve is brought to bear, is brought down, we can always expect that we will not find a steady state in our relationship with the environment. All right, so with that said, that's the baseline of energy. Humans are burning too much energy. Energy discharge is an exponential function. This is causing exponential change in the environment. And energy otherwise has remained balanced through evolution. And we are not in balance right now. So here's at least 3 reasons that the concept of energy is considerably more than just renewable versus non-renewable. And this is a concern. So what does this mean for design theory? Modern design theory is to provide goods or services with increasing efficiency, use less water, use less energy, use less materials, make it cheaper, make it easier on the environment, right? This is modern design theory. This is what we teach here in our engineering colleges. But this has a systems theory outcome that we've been aware of since the mid-1800s, but we now have decisive data. And that's that when we improve efficiency, This results in increased rather than reduced energy or resource consumption. These innovations allow the technologies to be more profitable with lower prices, leading to increased demand. In fact, the graphs that we've been looking at from Stefan et al., age of acceleration graphs, depict this, what is otherwise known as Jevons paradox. As we improve efficiencies, we are not improving our resource and materials consumption, materials and energy consumption. We're actually making it worse because we're making those materials available for someone else. We're not returning them to the environment. And the age of acceleration graphs that we've become known, that has become standard in sustainability discussions from Stefan et al. Are the perfect example of this Jevons paradox. So where does that leave us? If design theory, the modern design theory to increase efficiency is no longer applicable, then the only path for sustainability is to flatten this energy curve. It's not to have clean energy, it's that energy itself, the discharge of energy, is causing change to the environment. And this leads us to address the incommensurability thesis that's been put forth back in the 60s, and then it's been republished a couple of times here over the last couple of decades. The structure of scientific revolutions is that when a new paradigm cannot be proved or disproven by the rules of the old paradigm, and vice versa. Okay, we, with our current society and our dependence on this energy, can't imagine life with energy back here, the energy consumption, say, before 1850, a balanced biosphere energetically for all species and for humans as well. This is known as an incommensurability. We can't explain it. We can't imagine making the changes necessary to flatten this curve. And this implies that a scientific revolution is upon us. If you have any questions, I encourage you to reach out to me. And again, this is a paper that we're currently preparing to submit. So you'll be able to see it soon. I appreciate the audience and look forward to hearing any comments you might have. Thank you.